Determining how the seafloor changes over time has given scientists information about the... Alright, so if you remember our seafloor spreading method here is what we get heat rising from the asthenosphere, and this heat is thinning out and pushing apart the crust at a divergent boundary, and as it thins and thins, eventually new magma comes to surface and forms new seafloor, and you get a rift valley like the East African Rift Valley or the Mid-Atlantic Ridge. And then eventually we get an ocean, and we have like an older seafloor over here and a newer seafloor in the middle. And so determining how the seafloor changes over time has given scientists information about the circulation of solar energy. No, it's talking about circulating energy in the asthenosphere inside the Earth. Patterns of carbon movement. No. Formation rates of the ocean crust. Well, that's exactly what we're talking about here with the formation of new seafloor is the formation rate of the ocean crust. So our answer is C. This map you see is a really interesting and very useful little map for scientists who study plate tectonics. What you're noticing here is all these little red dots, and each of these red dots represents a volcano or seismic activity such as an earthquake. And when you go and you put all these dots in all the places on the world, what you end up seeing is very specific patterns. And these are your plate boundaries. And the big one you see right here in the middle of the picture is the Pacific plate. This is known as the Pacific Ring of Fire. Alright, so let's look at the question. Which provides the best evidence for the theory that faults and volcanoes, earthquakes and volcanoes, are the result of tectonic plate interactions? Faults on tectonic plates are in constant motion, alright, but volcanoes may not erupt for many years. This may be a reasonably true statement, but it's not answering the question. Faults and volcanoes existed long before there were tectonic plates. That's just wrong. Tectonic plates that have many faults do not usually have volcanoes. That's just wrong. Faults and volcanoes are often found at tectonic plate boundaries. Yes, plate tectonic boundaries. That's where you're going to find most of your action for mountains and volcanoes and earthquakes. So our answer is J. This picture is a model of how the theory of plate tectonics came to be. So the theory is that we have this very incredible heat source in the core of our Earth that's resulting in very hot magma upwelling or rising to the top. And as it rises to the top, it cools, and then remember, cool things sink, and then hot things rise. And this constant movement of heat rising and cold sinking is called convection. And convection is our motor for plate tectonics. So let's look at the question. The Earth's mantle is made up of very hot material that rises to the top of the mantle, cools, then sinks, reheats, and rises again, constantly repeating the cycle. This action, which causes the Earth's crust to move, is known as, and our key word here is A, convection. So convection in the mantle is the whole theory of plate tectonics. In the early 1900s, Alfred Wegener proposed the theory of continental drift, and he had a lot of evidence to support it. One of his large pieces of evidence was a fossil Mesosaurus. It was an animal that lived right here on the coast of South America as well as on the coast of Africa. His theory was that there's no way that this exact same animal lived in the exact same place at the same time if the continents were where they are today. So he proposed a theory that the continents were all together, and that would explain why you would find the same fossils all over these places. Now, another part of his theory was that these rocks would line up. So he would study the layers of rocks in North America and Europe, as well as in South America and Africa, and he noticed that the rock layers lined up. And part of his explanation was there's no way that you'd have the exact same rock layers in the same places if they were not all connected at one time. So let's look into the question. Identical rock types, identical fossils, and very similar mountain ranges are found on different continents that are separated by a wide ocean. Which of these best explains these observations? F, organisms traveled between these continents on land bridges. That's ridiculous. The same forces erode mountains in different locations. These continents were joined together at one time in the past, And that's the best explanation, that these continents were once all together in a supercontinent called Pangaea. So H. You're looking at a picture of the waves of an earthquake. These are first arriving waves are called your primary waves, and then after your primary waves, the secondary waves arrive. The sooner the secondary waves arrive, the closer you are to the earthquake. The longer it takes for the secondary waves to arrive, you can kind of tell then how far away you are from the earthquake. Alright, let's look here at this picture. We see R. We see an earthquake has occurred under the ground. Remember, the key word here is this is the focus, the place under the ground where the earthquake occurs. If you draw a perpendicular line straight up to the surface, this is your epicenter. This is where the destruction and the waves are going to be the strongest. If we notice, house X is much closer to the epicenter, probably in more danger, than house W, because it's farther away from the epicenter. So the question is asking you, which of these graphs is correct? Alright, so look at the arrival time of the waves at house W and house X. Would the waves arrive at the exact same time? No, it's going to take longer for the waves to get to house W because it's farther away. So here they're arriving first in house W, so that's wrong. Here they're arriving second in house W. That is absolutely correct. So our best answer here is H, because it's going to take longer for these waves to reach location W than it is location X, because location W is farther from the epicenter. A volcano eruption occurs when an underground chamber of magma reaches the surface, and all the dissolved gases inside the magma can make it very explosive and cause an eruption. When this eruption does occur, you can see that there's a big gas release into the atmosphere. Gases include like carbon dioxide, sulfur dioxide, water vapor, hydrogen, nitrogen, but notice not oxygen. Alright, so let's look at our question. A volcanic eruption can affect the atmosphere by reducing the amount of water vapor in the atmosphere. No, it actually will add water vapor to the atmosphere. By adding large quantities of several gases, such as sulfur dioxide, to the atmosphere. Well, B is true. Let's check C and D. Clearing away nearby clouds, increasing the amount of sunshine. A volcanic eruption does not make a sunny day. In fact, it'll make a really dark, gloomy, cloudy day. Increasing the amount of oxygen due to escaping gases. No, it doesn't release oxygen. So our best answer here is B, adding large quantities of several gases such as sulfur dioxide to the atmosphere. Looking at this illustration, we see a very dense, heavy ocean crust made out of basalt being taken under this more buoyant continental crust that's lower in density, such as granite. And as it's being drug under, its own weight starts to pull it faster and faster. And as it reaches around 60 to 70 miles under the surface of the earth, you'll see that it starts to melt. And when it melts, it forms volcanoes, a long arc of volcanoes along the land. Alright, so let's look at our question. Each dot on the above diagram, so everybody sees all these dots, most of them are right where the two plates collide here, marks the origin of an earthquake. The area with the highest concentration of earthquake origins, right here, marks a line of the Earth's magnetic field. No. A seam of soft rock such as limestone. No. The path of the subducting tectonic plate. That's exactly what we see right here, the path of the subducting tectonic plate. So our answer is H. So our San Andreas Fault is a large crack in the earth here as a result of the Pacific plate moving northwest a little faster than the North American plate. So it's a very dangerous area, and you can see San Francisco is built right on this fault. That's why they have the potential to have very dangerous earthquakes in San Francisco. So what kind of fault is this when the land is shifting side by side? A normal fault, a reverse fault, a strike-slip fault, or a thrust fault? This is a transform boundary right here, a side-by-side action, which results in C, a strike-slip fault. So the answer is C. Alright, just a real quick review of the three types of faults. We've got a strike-slip fault, and that's where the land is shifting side by side. Alright, we've got a normal fault, which occurs when the land is being pulled apart by tension forces, and that's illustrated here by the two arrows showing a divergent boundary. And now, when this occurs, we see that it's normal for the hanging wall to just have gravity slide it down the footwall. And if you don't remember what those are, the footwall is the one that you could kind of see right here, you could easily walk up. The hanging wall is the one as you were walking up, you could maybe hang a light on it. Alright, so a normal fault is at a divergent boundary whenever the hanging wall is sliding down the footwall. Now at a convergent boundary, as illustrated by the arrows pushing together, converging, it would be more likely that the hanging wall here would be forced upward and slide up the footwall, kind of against gravity. So here's your hanging wall, here's your footwall, and the hanging wall is going up. Now the question's not that hard. This diagram illustrates which geologic process, and if you're really good, what you see is you can tell that the hanging wall is being forced upward. That must mean this is a convergent boundary, and this would be a thrust fault or a reverse fault. But the question doesn't even get that tricky. It just asks you what's happening here, and the answer is a fault. So faulting is the right answer. Alright, when two oceanic crusts collide, like the Philippine plate and the Pacific plate, the older plate, which is colder and more dense, will actually be the one that gets subducted or taken under, as we see right here, the Pacific plate is being taken under. Right where these two meet, you're going to see a little area where both are kind of going downward, and you're going to see a very deep part of the ocean, going to be called a trench. The best example of this and the deepest part of the entire Earth is the Marianas Trench in the Pacific Ocean. It's 36,000 feet below sea level. Now that's even deeper than Mount Everest is tall. Alright, and what's it caused by? Let's look here. The answer is D. Two tectonic plates colliding and one plunging below the other. That's what creates a trench. Alright, this picture is locating the epicenter of an earthquake. Now, the way this was done, a seismograph device in Detroit gave us a reading and said the earthquake was maybe 500 miles away. So the people from Detroit drew a radius 500 miles away from themselves. And now we knew the earthquake is somewhere along this circle. So what you can do is you can call a friend in Minneapolis, and the friend in Minneapolis said, yep, we got the readings of the earthquake and it was 800 miles away. So when they drew a circle, it intersected the line from Detroit right here and right here. Now that gives us two options. We know the earthquake was either here or here. The best, most scientific way to find out for sure where that earthquake was to call another friend. So we called Charleston, South Carolina. They tell us the same thing. We found the earthquake. It's right along this blue line, and all the lines are always going to intersect right at the point of the epicenter. So what's the fewest number of seismograph stations that must record the arrival times of P and S waves in order for the epicenter of an earthquake to be located? The answer is B. You need to triangulate it with 3 places. So B3. In this diagram, we have 2 continental crusts dividing. Now remember, both continental crusts are lower in density and fairly buoyant compared to a very dense oceanic crust. So what happens is one continental crust slides under the other continental crust, and it pushes the other continental crust higher while folding and deforming it. So you get a huge mountain range. But what you don't get is you don't get enough sinking to the point where you get melting. So there's really no volcanoes along this mountain range. It's just a regular mountain range without volcanoes. So the mountain shown is composed of deformed sedimentary layers. They are located near a tectonic plate boundary and are still increasing in elevation. So why would mountains still be going higher? The answer would be because the 2 crusts are still colliding. So A, colliding tectonic plates. Alright, what is the point of scientists marking all of these volcanoes and earthquakes on a world map? And if you do this enough and you mark every earthquake and every volcano, you will see very distinct patterns. And those establish plate tectonics, or plate boundaries, F. Earthquakes. Earthquakes are caused by the shifting of the earth. And that is usually caused from faults. Remember, like a reverse fault where the hanging wall slides up the footwall due to a convergent boundary. A normal fault where the hanging wall slides down the one that you could actually walk up, this guy here, the footwall. That would be at a divergent boundary. Or a transform boundary where the land is being shifted side to side at a strike-slip fault. So what's responsible for an earthquake? Pressure buildup in the mantle? No. Slippage along faults within the Earth's crust? Absolutely. That is the best answer, letter B. Before the theory of plate tectonics, there was the theory of continental drift, that the continents had moved around and were once all together in this supercontinent called Pangaea. The best evidence they had at the time for this was the fact that you could find this plant right here in Australia, Antarctica, India, Africa, and South America, all at the same time in history. Now, there's no way would this plant be able to thrive and live in the environments as to where the continents are today. So there was also some other animals that were found hundreds of millions of years ago living pretty much in the exact same locations of South America and Africa if you push the two together. And that also led belief in the theory of continental drift and then eventually the theory of plate tectonics. So the question here, the answer, the explanation of what he was trying to explain with this diagram was supported by the reason for similar fossils in Africa and South America. So our answer here is B. The reason for similar fossils in Africa and South America helped explain this diagram. A diagram of seafloor spreading occurring at a divergent boundary, because as shown by the arrows, pulling the land apart, and magma coming to the surface and forming brand new seafloor right here. And you can see the older crust is eventually getting subducted and melted under the continental crust, and then it gets recycled, and this process goes on, always creating new seafloor. Alright, so when seafloor spreads apart, volcanoes and ridges are formed because sediments are deposited where the floor spreads apart, building ridges. That sounds like such a good answer, but make sure you read them all. As the plates pull apart, magma moves to the surface, building ridges. That also sounds really good, so remember B. Ocean water pushes down the surrounding seafloor, pushing up the ridges. No. Underwater earthquakes lift the seafloor into long ridges. That one's not a good one either. Alright, so if you chose A, I understand what you were thinking, but that's not the right answer here. The answer is B. This has to do with plate tectonics and pulling apart of the plates and magma moving to the surface. So our best answer is B. The folding and faulting found in the rocks of the Blue Ridge Mountains of Virginia were created by, the trick here is it doesn't matter that it's the Blue Ridge Mountains of Virginia. The question is just simply like what makes a mountain? And mountains are caused by the collision of continental plates. That's its number one method here of making really grand mountains, and the Blue Ridge Mountains are an example of the Appalachian orogeny, which occurred during the formation of Pangaea hundreds of millions of years ago. So the answer is A. The theory of continental drift in the early 1900s was the theory that all the continents were once together into a supercontinent called Pangaea, and that they are drifting apart. The two major pieces of evidence that was used to support this early on was the presence of similar fossils on multiple continents that, as the continents are today, these fossils probably wouldn't have been able to thrive in those environments. So they were probably in the same environment. And also the presence of land animals in continents that are now separated by a very, very far ocean. Alright, so all of the following, make sure you see the word except in italics here. The continents seem to fit together like pieces of a puzzle. That was a good piece of evidence. There are similar fossils on different continents. Good piece of evidence. Mountain ranges in South America and Africa line up. Absolutely. It does look like this is the same mountain range here in North America and in Europe. The North Pole and Antarctica are covered with ice. This is not evidence. It's a true statement, but this is not evidence to support continental drift. So the answer is J, since it's wrong. Plate tectonics has to do with three major concepts. We've got the land being pulled apart, where we get a divergent boundary and we get like new seafloor being created. We get land smashing together at a convergent boundary, causing subduction and melting and volcanoes. And we also get land shifting side by side at a transform boundary, resulting in earthquakes. All right? So our three major results of plate tectonics are earthquakes, mountains, and volcanoes. Now, what we don't get as a result of plate tectonics is limestone being eroded away by groundwater, causing caves, caverns, and sinkholes, such as karst topography. So which of the following is not an example of plate tectonics? J, karst topography.